Alright everybody, and welcome to this video. Today we're going to be looking at Thevenin and Norton circuits. These are just going to be a few concepts, then we're going to move on to some problems in the later videos. Okay. So these are just a few concepts from the SI session number 5. Okay. So what is Thevenin and Norton? So Thevenin and Norton is a way to quickly analyze circuits that you make changes to. So say if you were to take a circuit, then you had a certain resistor in it, and they wanted you to find like the voltage across that resistor. So you find all the analysis, and you find the voltage, but then they change that resistor, and they say, okay, well, what's the voltage now? So you had to redo the entire analysis because your entire circuit changes. Well, what Thevenin and Norton allow you to do is to create a simplified circuit that prevents you from having to do all the analysis completely over. Okay, so that's kind of like the general background of Thevenin and Norton circuits. But let's go and take a look at Thevenin. So Thevenin is going to involve a voltage source that we call Thevenin. We will have this resistor that we call Thevenin. And we have two open terminals, one with a positive, one with a negative. We call this VOC, where OC stands for open circuit. Okay? And what this means is that if we were to go and drop a wire across that open circuit, now this would allow current to be induced. And it would have a voltage across here, so the voltage difference. Okay, so this will be in series, where you have Thev and Thevenin. Okay. Now let's go look at Norton. So Norton is a current source. Okay. Go. But now this is going to be in parallel with the Thevenin, so it's the same Thevenin as before, where we have our plus and minus terminals, where this is still VOC. This is an open wire. And this current source is called Norton. What this does is that this circuit is saying, okay, since this is open right here, the current that leaves this battery source can only loop around right there. But if we were to, say, go and drop our wire right there, like we did before, now our current will come up through here, hit this point. It recognizes it can either go down this way or go down this way. And we know that current wants to follow the path of least resistance. So you have a resistance here, or you have an open wire, or I'm sorry, closed wire with no resistance. So the current will bypass that branch and make a big loop around that way. So what we call up here, this current that was induced, this is I short circuit. So I will write I short circuit there. We call this current right here I Norton, but we notice that the current running through that blue wire is I short circuit. Same current. So we know that I Norton is equal to I short circuit. And we still have the Thevenin, and we have an I Norton. Okay? But these are going to be in parallel. And how do we relate these two, though? We'll use Ohm's law. So V is equal to IR, where we will write the Thevenin is equal to I Norton times Thevenin. And that goes for both cases. So this is how we get back and forth between these two. Okay. So how are you finding these? So this is going to be the case most of the time where you don't have any dependence. Okay. So dependent sources are the sources that look like diamonds. Okay. And these are sources where you'll see like 0.5 like V of A, or this would be like 4IX, stuff like that. So you see that the amounts of whatever they're delivering is dependent on something else in the circuit. So step one is to identify if we have any of these. If we have any of these, we can't do it. But if there are none, so there are none, so all right, no dependent sources. I'm going to shorten dependent with DEP. Therefore, we can zero out sources in the original circuits. So what that means is we'll go to the original circuit, and everywhere that we see a battery, we'll take it and we're going to replace it with a regular wire. And everywhere we see a current source, we're going to replace it with a broken out section of wire. So open terminals, we'll basically clip it out of the circuit. Okay, so that's step one. Step two involves finding our Thevenin. Okay, so what that means is that we're going to treat VOC like a battery. And then we're going to then find our equivalent with respect to VOC. Okay? So what that means is, typically we have like this setup. Where we've got like resistor here, resistor here, resistor here, and there's like one right there. But now what we're gonna do is do something like this, where we will have our open terminals. Now this will be VOC. We're going to act like it's a battery. And we're going to take our equivalent going that way. So typically, we usually work that way for our normal circuits, but now we're going to be working left to right. Okay, and we're going to break it down to where there's only one resistor, which is our equivalent. Okay. And when we find our equivalents, that is going to be equal to our Thevenin. Then step three will be to find I Norton or V Thevenin using previous methods. Okay. And by previous methods, we mean, nodal analysis. You really don't see mesh loop very often, but mesh loop can be in there, KCL, KVL, just regular old Ohm's law. Current division, voltage division. The list goes on. But we're going to use all of these previous methods that we used for exam 1 to find one of these values. Okay, and we're going to see that in these problems in the following videos. So I will see you over there.